continue with circle geometry. We have proved some theories in the circle about the center, angle in the center and this angle in the circumference, about the angle in the same segments, about opposite angles of cyclic quadrilateral and the exterior angle of the cyclic quadrilateral. Now this part is not always emphasized, but very useful. You might not prove it, but when you come across it in the examination, yes, you've figured your way out, but it might be slow. At the same time, it's useful in other aspects of STEM, like mechanics, physics, waves, simple harmonic motion, vibration, etc. So I like you to, concentrate from the beginning to the end. It might be something you have known before, or it's something that when you come across it in your exam, you can easily find your way out. But it's good you know it, at the tip of your finger. So once you come across it, you can easily work your way out. Now, before you go into the circle per se, I would like us to, revise some small aspects. I would like us to revise small aspects of some things about triangle we have known before, and angles. If you have parallel lines like this, and we have intercepts like this, this one is parallel to this. You know that this angle will be equal to this angle, vertically opposite angles. This angle will be equal to this angle, alternate angles. And this one are equal, corresponding angles. Please take note. Vertically opposite, alternate, corresponding, they are equal. That one is solved. Then, let's look at some triangles. Now, if we have isosceles triangle, it means that this place and this place are equal. Automatically, this place, this angle and this angle, they are equal. In essence, if we draw a vertical from this place and we cut it into two, we let this place have right angle and this place have right angle. You see, they have this one as common. By the time you look at this angle and this one is equal. This angle and this one are equal. Automatically, this one and this one will be equal. What does that imply? It means that the initial angle here has been cut into two. But you see, if we had theta here before, we are having theta over 2 here. We are having theta over 2 here. So, which means that this perpendicular divides this angle equally into two parts. And again, by the time you look at it, this one is common. This one and this one is equal. We have similar triangle now. Similar triangle. So it means that this place and this place are equal. So what are we trying to say? If we draw a vertical line from isosceles triangle to the base, if it is perpendicular to the base, it will cut the base into two equal parts. Now, another type of isosceles, you can say equilateral is a type of isosceles triangle, which means that all of these are 60 degrees. Fine. But when we draw a vertical like this and we cut it like this, it means it will give us 30 here, 30 here. This place will be equal to this place. Simple. So we have been able to talk about two major things now. About the angles, corresponding alternate angles and vertically opposite angles. We also talk about cutting a triangle, isosceles triangle, but by perpendicularly into two. That one is solved. Now let's go into, if we have another triangle which is not, well, that one might not come. Let me leave it like that. Now let's look at congruent triangles. When we are talking about congruent triangles, we are saying that these two triangles are equal in size and all the angles are equal. That if we have two triangles like this, this place, and this place is the same thing as this place, and this place. That is congruent. In the same vein, if you have this angle here, the same as here, you can see the place here. This one has the same thing here, and this one now has the same thing. So what does that imply? It means that this one and this one, they are image of each other, and all the opposite sides and the angles, they are equal. So But you don't need to give the 6 conditions to know that 2 triangles are congruent. You just need 3 conditions. Just 3 conditions to know that the triangles are congruent. The reason I'm talking about congruent triangles now is that in proving the theory or the theorems, the later theorems I'm going to prove or talk about, once you know about this, I won't need to write much. I won't need to go into lengthy proving. So once you know about this, in case you come across the proving or you come across the theorem, it will just, flash before your face and you remember it. So take note of congruent triangles. So with this, we'll be able to solve or prove our theorems without much or lengthy talk. Now, let's talk more about congruent triangles. This is another topic, but I just need to bring it in as a reminder for ease of the topic. When the corresponding sides are equal, like I said initially, you don't need to give all the 6 conditions. 3 conditions, you can prove that 2 triangles are congruent. Automatically, when you know that this place, and this place, so you have another triangle. Either this place, and this place. Either way you turn it. If you can have the 3 sides to be equal, you understand? If this place is equal to this, if this place is equal to this place, this place is equal to this place, this place is equal to this place, they are congruent. That is what it means. So this one has taken place. So you always represent this one as S. You understand? That was the first condition. Now the second one is when these 2 sides and the enclosed angle are equal. So if you have 2 sides like this, I will not turn this one, but in case it is turned, you will know. So and you have another one like this. You have an angle here. So this one is theta. This one too is like this, and this one is theta. By the time you consider trigonometric ratios or rule, like cosine rule, sine rule, by the time you combine this one and this angle, automatically this one and this one will be equal. So it has already given us congruence. So if you have it like this place and this place will be automatically equal. So once you have this condition, this one, but note, the angle given must be between the 2 sides. So if this angle here is here now, and you have this place equal, no. So it must be between the 2. So that one is gone. Don't let me waste time here. This one is already settled. So the last one we did was SAS. That is the 2 sides and the included angles are equal. So this one is ASA. That is the 2 angles and the included sides are equal. Now look at this. This angle is equal to this. This one is equal to this. So if you look at this, automatically it means that this angle will be equal to this angle here. Fine. And once you have it like this, by the time you apply sine rule or any other trigonometric rule as comes to your mind, it will show you that you will know that this one will be equal to this one here. This one will be equal to this one because they are facing same angles. So once you have 2 angles and an included side, ASA, the triangles are congruent. Fine, we are about to do that. Now let's look at the last condition now. It says if the 2 triangles are right angled, they are hypotenuse, and one other side are equal. So look at this. You have a right angle triangle. Hypotenuse is equal, and another side is equal. So this is the right angle. Hypotenuse here. Either this one or this one is equal. So let's make this one equal to this one. So let's make it like this. So it means that this place is equal to this place. This place is equal to this place. So you see, is this one where external angle? You know the other one, the angle must be between. You understand? But in this instance, if this one and this one are equal, that is the hypotenuse, are equal, and this one is equal to this one, automatically, by the time you apply either cosine rule, tangent, sine, you will get all the sides. And by the time you calculate the sides, they will be equal. Because by the time you do this, even if you apply Pythagoras theorem, you will get this place. By the time you apply Pythagoras theorem again, you get this place. And the 2 are equal. So note this one, RHS. We have SSS, SAS, ASA, and RHS. That's all. So from here, I can quickly run through the circle theorems or circle geometry. Let's go on. Now let's look at this theorem. It says a straight line drawn from the center of a circle to the midpoint of a chord which is not a diameter, it's a right angle to the chord. That is one. The corollary, that is, in another way, if you look at it, we can say that the perpendicular bisector of any chord passes through the center of the circle. Because if it comes through and it cuts it into two, the next one, another theorem that you can deduce from it is a straight line drawn from the center of a circle perpendicular to a chord bisects the chord. I want you to have the picture of that triangle, isosceles triangle I drew initially. Now let's go to it. If you have a circle and you have the center here, the diameter will pass through the center, so you can't draw any line from the center to cause to bisect the diameter because it's already at the center. Now let's draw. Now fine. From this place to this place is radius. From this place to this place is radius. So we have isosceles triangle automatically, and this is a chord. So if we bisect it into two, like I showed you initially, this will be a right angle, this will be a right angle, and this one will be equal to this one. I've deduced that one initially. So we don't need to stress ourselves in talking about it. So if you come across this, you have to prove it. I have done that one with the isosceles triangle initially. Now from this one, it is now telling us that if we now have any perpendicular bisector, that is, it is at right angle here. Anyhow it moves, it must pass through the center. If you have a perpendicular bisector from a chord, it must pass through the center. Like this one now, if you have it here, and we have a perpendicular bisector here, it cuts it into two equal parts. It must pass through the center, in as much it is a perpendicular bisector of the chord. So you can see we have talked about the two, about the theorem, the corollary. Now let's talk about a straight line drawn from the center of a circle, perpendicular to a chord bisects it. That has also been shown here now, like I did with the triangle initially. In as much it cuts a chord perpendicularly like this, it bisects it, because we have the picture of isosceles triangle. And so once it comes here, because this one and this one, they are equal. And by the time it cuts this one, it bisects this angle, and it bisects this side too. That's all. So you know how to put it into writing. I don't want to waste time here. Now let's look at another theorem. So before we go into another theorem, I would like us to look at it again. We have this one, first one. This is the chord, and this is the center. It says this one. So we have isosceles triangle. Now it says it's at right angle to the chord. So if we draw this one now, we have this one. That's the first one. We have explained. The next one is saying that if you have the chord here, and we have, so these ones are the radial. So if you should come, and cut this one like this, you understand? It must pass through the center. That's what we are saying. That is the second one. The third one is saying that a straight line drawn from a circle, from the center of a circle, perpendicular to a chord, bisects it. Now we are now saying this is the third one. That if we have a line like this, and it passes through the chord, if it is perpendicular, it means it cuts it like this. It cuts it into two equal parts. So that is what that means. But if it cuts it like this, the angle between that line that comes from the center of the circle to the chord must be 90 degrees, right angle. That one is clear. Now, let's look at this theorem. It says equal chords of a circle are equidistant from the center of the circle. Another way you can put it is chords that are equidistant from the center are of equal length. Now look at this. We have one circle. We are talking about the same circle here, please. And this is the center of the circle. You have a chord here. And we have another chord here. And we are saying that equal chords of a circle are equidistant from the center. Let's say this one is equal to this one. You see. Now, you have isosceles triangle. Again, you have isosceles triangle. You can see, you have isosceles triangle, you have isosceles triangle. And this one is equal to this one. So we have 1, 2, 3. This one is equal to this one. So 1, 2, and 3. Because this one is equal to this one. This one is equal to this one. So this one is equal to this one. You see? And by the time you look at it, we have congruent triangle. If I say this one is A, OAB, OCD, this one is equal to this one. This one is equal to this one. So it means that triangle OAB is congruent to triangle OAC. OCD, sorry. And since this happens, if I should draw any perpendicular from the center to this one, it will be the same thing here. You understand? So in this situation, it has shown that if the chords are the same distance from the center, they must be equal. And at the same time, we are saying that, okay, if the chords are equidistant from the center, they are equal. If the chords are equal, their distance from the center will be the same. That is the actual theorem. If the chords are equal length, their distance from the center will be the same thing. So that is proven. You don't need to do so much talking. Now let's quickly talk about secants and tangents. Secant is a straight line which causes a circle at two distinct points. So let's look at, if you have a circle like this, and the line cuts like this, you can see this line that comes from the outside and cuts through the circle and extends beyond. That is what we call secant. But from this point to this point, we have what we call chord. So now look at this. This is a chord. It is within the circle. It is not cut out. But this is secant. It extends beyond the circle and it came from outside the circle. So that is secant. Now, we talk about tangent points. Where secant touches the circle is called the point of contact or point of tangency. That is the tangent points. So, tangent points, that is the point where the secant just touches the circle. It touches it. Like now, you see the secant now. By the time it comes here, it gets smaller. That is the chord will get smaller. And it gets smaller. At a point, it will just touch the circle at one point. That is the point of tangency or point of contact. This is point of contact or tangent points. So that is the point we are referring to. But in this instance, this secant is now referred to as tangent. This secant now that just touches the circle and goes away at one point is referred to as tangent. And you can see this point at which it touches the circle is very small. Very, very small. So if you draw any line from the center to the chord, to the tangent, you can see it is very, very small. So by the time you look at it, it cuts this place into two equal parts, just like it cuts the chord. So you are going to have it like this. Now, so angle between a tangent and radius of a circle is 90 degrees or right angle. So from the center to the tangent, whatever the line is, the angle will be 90 degrees. So that is how simple it is. The size of the line of the point is very infinitesimal. So any line that cuts it, it has no choice but to be 90 degrees. From the center, from the center. That is what you are saying. Now that you have known about secant and tangent, we can now talk more about the theorem. The straight line, which is drawn at right angle to the radius of the circle, at its point of contact is a tangent of the circle. So what we are saying is this. If you have this, and you have another straight line like this, and by the time we draw a line from the circle, center of the circle to the line, and it is at right angle, you can see at the point of contact that this is a tangent. You can see the straight line which is drawn at right angle to the radius of a circle at its point of contact is a tangent to the circle. That is it. Now, from this we can also realize that the angle between the tangent and the radius of a circle drawn through the point of contact is 90. That is what we use to define. That's what we use to define the tangent. Another thing you can say is that the perpendicular to a tangent at the point of contact passes through the center of the circle. So which means that you might have another line from it. If it is not at right angle to it, it does not necessarily pass through the center. But if it is right angle to it, it will pass through the center. So that's what we use to define the tangent. So sometimes we call this one normal. You know, when you have a line. So the one that is perpendicular to it is the normal. So normal, radius and normal to the tangent. That is it. Or radius and normal to the tangent. That is it. So with this, we have covered secants, and tangents. Let's look at another thing that we can now generate from this. Now we have established that the angle between the tangents and the line that passes through the center of the circle or the radius must be right angle. Now, let's look at this theorem. It says if two tangents are drawn to a circle from given point outside the circle, then the tangents are equal in length. Another thing you can know is that the tangents obtain the same angles at the center of the circle. The angle between the tangents is bisected by the line joining the center to the external point. So what are we saying? If we have a circle like this, and then we have the point outside, what we are saying is that this one will be equal to this. Now let's prove it. You see, so this one is right angle, this one is right angle. And let's join this. So we know that this one and this one are equal, radius. This one is right angle, this one is right angle. You see, and this is the hypotenuse. Remember from our discussion on congruency, we talk about the last condition, which is RHS. That is right angle, hypotenuse, and any other sides of the triangle being equal. So if you look at this, you have hypotenuse common to the two. That one is equal. Okay. This one, right angle, common to the two. And the two sides, and we have two sides which are also equal. So this condition, RHS, is fulfilled here. And if that is fulfilled, it means that the triangles are congruent. Now we have hypotenuse, this side. Automatically, these sides too must be equal. And these are the tangents. Tangents. That is it. And they are from the same point outside. So we have proved that the tangents from the same point outside the circle to the same circle will be equal. That one is done. Now by the time you look at it, this one is equal to this one. These angles are equal. The hypotenuse is equal. So automatically, by the time you use sine rule, cosine rule of tangents, and sine ratio, cosine ratio, and tangent ratio, you will realize that this angle here and this angle here will be equal. Because if you look at it, let's say, okay, this is hypotenuse, and let's call this one. So if this is hypotenuse, this one is facing that. This will be the adjacent. This angle. So, which means that this one is theta here, and this one is theta here. So that one is already fulfilled. Because by the time you make it, for this angle and this angle, it's going to be cos theta will be equal to. So, and it is equal for these two triangles, so this one is fulfilled. Now, by the time you look at this, the three angles here must be equal to 180 degrees. The three angles here must be equal to 180 degrees. By the time you sum this one and this one, and subtract them from 180, it's going to give you this. The same thing, because this one and this one are equal, this place will be also the same. So we have talked about the three conditions. You can see, very simple, but it's good you know them. So whenever you are doing any work later on, you'll be able to solve them without stress. Now let's talk about intersecting chords, secants, and tangents. Here, we will put what we have learned before in circle theorem into use. But before we do that, I'd like to remind you about similar triangles. When we have two triangles that we say, two shapes, we say that they are similar. It means that the sizes are in constant ratio. The sides are in constant ratio. Now let's look at this. We have this one, A, B, and C. D, E, and F. So if we are talking about similar triangles in this instance, it means that A over D is equal to B over E is equal to C over F. But one thing that is common to them that you will know is that all the angles will be the same. But the sides are in constant ratio. That is the thing. But if it is, what is it called? Congruent. K will be 1. It will be the same. Now, How do we now establish that two triangles are equal, are similar? The condition is, when you look at the angles, you can see that all the angles are equal. It means that the corresponding sides will be in specific ratio. Now look at this. Since I have known this to be the fact, and I don't know F and E, but I know A, I know C, and I know B. You understand? But I can establish from this fact, this angle here, that they are similar. It means that I can find E and F now, because I have known the ratio of this one to this one. So I can use that to find the ratio to find F. I can use the ratio to find E, like this. So if I can establish that, that is all. And I can also look at it. Once I can look at two sides and included angle and whatever, I can say, oh, these triangles are similar. So from there, I can work it out. So we are going to use the principle of similar triangle in this intersection of chords, seconds, and tangents. Sometimes you can have seconds and tangent to, interact. Chords and seconds, chords and tangent, whatever. But when we get there, you will see. And with this already in mind, we find it very easy to tackle. Now, we want to establish the relationship between these chords, the length of these sides, from where they intersect. Looking at this, you can start doing something. You can see. And now, I can also do this here. Now, you can see that angle C and B, they are in the same segments. So this one and this one are equal. You understand? By the time you look at it, this one too here and this one here, they are equal. You understand? So, we have triangles IAC and triangles IBD. So from this fact now, we can see that they are similar. They are similar. I is not the center, So we can see that they are similar. This angle is equal to this one. This one is equal to this one. So you can see that this one is similar to this one. Now, let's look at it. From this fact, okay, let me also just put this one here for fancy sake. You can see that AI faces angle. Let me call this one alpha, alpha, beta, beta. If you look at it, AI faces this angle, ID faces this angle. So now that we can establish that triangle IAC and IBD are similar, we can now conveniently say that AI over CI is equal to DI over BI. You can look at it like that. Or you can say CI over BI is equal to AI over DI. Either way. Now, the most important result we are going to achieve is that AI times BI is equal to DI times CI. So, what are we saying? That if the two chords cut at the points, the product of the two parts will be the same. The product of the part that is cut will be the same. That is, this is the chord, and it's cut at the points here now. The product of these two parts, CI and DI, will be the same thing as AI and DI. So that is what, this is also very good and very important as well. Let's look at another intersection. Relationship between intersection of the chords. Okay, let's see. Let's look at this. The chord is extended beyond the circle. Or you can also refer to it, for me I'm looking at it as seconds. Now, we want to look at it. It came from the same point outside. Now let's look at how the relationship between the chords or seconds will go. Now let's do something. you can see that this one and this one, they are in the same segment. You can see. So which means that this place and this place are equal. Let's call this place alpha, alpha. Let's call this place theta. Now look at it. We have several triangles, but let's pick two of them. Triangle A DI and triangle CBI. Looking at these triangles, you can see that ADI and ADI, yes, and CBI. By the time you look at it, if this is alpha, this is theta. By the time you subtract the sum of this from 180, let's call this place beta. This one is also alpha and this one is theta. It means that this place will also be beta. So we are having similar triangles. Now, we have two similar triangles here now. Triangle ADI and triangle CBI. We have these two similar triangles. And by the time you look at it, we can now say, since this place is facing this angle here, we can say that side CD, CI, this one, are you getting it? Over this one, over AI. Because the two of them are facing this angle in their respective triangles. Is equal to BI, okay, CI over AI, is equal to BI over DI. When you look at it, the two of them are facing the same angle. This one, BI, is facing alpha, and DI too is facing alpha in its own triangle. So, by the time you look at it, you can now say that CI times DI is equal to AI times BI. Please take note of where we take the respective length to multiply. This AI is from this point to the external, from the lower point of the circumference to the point of contact. BI is from the upper point of the circumference, where it cuts the circumference, to the point of intersection. The same thing happens, CI, that is this one, from this lower point to the point of intersection, and DI from the upper point of this same chord. So that is, so we have done two about the intersecting chords, or tangents and then secants. Now let's look at another one. Now let's look at chord and tangents. If you look at this, let's call this angle alpha. We call this one beta. By the time you work this out, you will realize that this angle here is equal to this angle here. You understand? This angle here is equal to this angle here. Alternate segments. We will prove it. Beta, angle C, angle B, CI is equal to angle CAI, alternate segments. We'll prove that after this. So this one and this one are equal now. We have already gotten that. But this one and this one are equal. So we are looking at two triangles. Triangle C, AB, and triangle C, then we call it triangle B, C. Sorry. Now we are looking at triangle CAI and triangle BCI. Now, if you have gotten this, you will realize that this angle here will be equal to this one too. This one here will be equal to this one. By the time you add this and subtract from 180, it will give you this. Adding this one and this one will be the same because the two angles are equal. Now we have already gotten our triangles CAI and BCI. Now, let's look at the similar sides. If you look at this, AI is facing angle gamma and TI is facing angle gamma. So we can now see AI over TI will be equal to, let's see, which one is facing angle beta? It means that ti, because that is for angle ti over bi. So you can see. So we can now say ai multiplied by bi is equal to ti times ti, which is equal to ti squared. So you can see, it's also like same thing with the other one too. The product of this place and this place is equal to this place times itself. That is all. So we have established the relationship, three relationships for intersecting chords or tangents and chord secant or whatever. So this is already solved, and that is, at least I believe you can, with what you have done now so far, be able to solve any circle problem. So as I promised, let's look at the alternate segment angles. Now, before I go to the theorem per se, I want us to look at what alternate segment is really. Now, when we say it is alternate or opposite to it, that's what we are saying. Look at this chord. Let me label it. Let's call this one called AB. And this one is called CD. And there is a tangent at this point. There is a tangent at this point too. The angle between the chord and the tangent here is alpha. The angle between the chord CD and the tangent here is beta. The segment that is after the angle here, we call it the alternate segment to this angle. This one too is the alternate segment to this angle here. So it is opposite to the side of the angle and the tangent. So since we have understood what we mean by alternate segment, let's go into the theorem per se. Now since we have understood what alternate segment is, we can now handle the theorem. The theorem states the angle between the tangent and the chord is equal to the angle subtended by the chord in the alternate segment. Now let's look at it very well. We have a circle, we have a tangent, and we have a chord. And we are now trying to prove that the angle here is equal to the angle here. That's what we are trying to prove. Now let's call this place alpha. Let's call this place beta. It is the angle in the alternate segment. Let's try to prove it. Now let this place be the center of the circle. And let's draw a line to pass through the center. By the time we've done this, we realize that this place, from our previous knowledge, that this place is 90 degrees. Angle in the semicircle. This place is 90 degrees. Because this one is the half of this one, and this one is 180 degrees. So this place is 90 degrees. Now, if this place is 90 degrees now, let's call this place gamma. And if this place is gamma, this place will be 90 minus gamma. Okay. But let me make this place alpha, beta, gamma. Let's call this place theta. So from here, we can see that theta plus gamma plus 90 is equal to 180 degrees. So we know that theta plus gamma is equal to 90. Because this is 180 minus 90. So this one and this one is equal to 90. Note also that the angle between the line that passes through the center of the circle or radius and the tangent will be 90 degrees. Remember this one too, from that tangent theorem. So we can now say that theta plus alpha is equal to 90 degrees. So what does that imply? It implies that alpha, gamma is equal to alpha. And you have established that gamma is equal to alpha. Note also something, that beta and alpha, they are in the same segments. Beta is equal to, beta and gamma are in the same angle, in same segment. But gamma is also equal to alpha. Therefore, beta is equal to alpha. So we are proving that, which means that angle in the same segment, angle in alternate segments, they are equal. So we have already proven that. Now let's look at this side too. If it is in this side. So we have already established that alpha is equal to beta now. So this angle here too, we want to establish that it is equal to this. That this one here is equal to this. Now, let's see how we go about that. Let's call this one angle A. call this one angle A. And then we can say that angle A plus beta is equal to 180 degrees. Opposite angles of circle quadrilateral are supplementary. Opposite angles of so this one and this one are equal to 180. But we also know one thing, that alpha here, this one and this one will be equal to 180 degrees. Angle on the straight line. Let's call this one B. From this place to this place, let's call it B. So alpha plus B, alpha plus B is equal to 180 degrees. Angle in a straight line. So what are we now trying to say? But alpha is equal to is equal to beta. Alpha is equal to beta. So let me just start again. Now let's look at this. A and B and beta. I want to use Greek numerals for the previous one and our normal alphabet for this one. A and B. A and beta, please. A plus beta is equal to 180 degrees. Opposite angles of cyclic quadrilateral. And let's call this place D. We can also say that D plus alpha is equal to 180 degrees. Angles in straight line. So D plus A plus alpha, is equal to 180 degrees. But we have proven that alpha and beta are equal. Alpha is equal to beta. Angles in alternate segments. Therefore, D plus beta is equal to A plus beta. Since alpha is equal to beta, which is equal to 180 degrees. Therefore, D is equal to A. You can see. So this one here will be equal to this one here. So we have it as angle in the alternate segments. So let's show it how it will look like. So in case you come across anything about alternate segments, this is how you recognize alternate segments. For this one now, so what does that imply? It means that this one will be equal to this. That's how you recognize alternate segments. So this one, let's say this is alpha. This place will be alpha. For another type, are you getting it? So which means that this place, beta, is equal to this place. So you can see, that's how you recognize angles in alternate segments, which are equal. Now let's talk about interaction between two circles. The interaction can be almost four kinds. Let's talk about one. Let's talk about one. Intersecting circle. It can be more than two sometimes, but the relationship between two, you have to take it in twos to be able to solve the whole thing. Now if you have two circles like this, that is, one has entered the space of the other one. We know that they have common chord. They have common chord. And the centers would have come together closer than the sum of the radii. If this is center A, center B, by the time you check it, distance AB will be less than RB plus RB. That is the radius of A and B, the sum. So it has come closer. So with this, you'll be able to do some calculations. If you know the distance total distance, you can do some calculation. You can be able to calculate the length of the chord. You can be able to calculate the perpendicular distance of the radii, because sometimes one radius, one circle might be bigger than the other one. So like this one now. You see? So it means that the radius of this one might be here, the radius of this one might be here. So the radius, the sum of the radii does not necessarily mean, or I mean, this distance does not necessarily mean it is perpendicular distance. You understand? So you are going to have something like this as perpendicular distance. So you can have so many things to calculate, but just know that this is one of the ways it can interact. You can have intersecting circles, and then you have the common chord. And due to some manipulation and calculation, you can be given some data, and then you'll be able to do some other calculations. Maybe the distance apart, the perpendicular distance apart, the length of the chord, anything can happen. So just know this is one of the ways the circle can interact. So intersecting circle. Now, as you have intersecting circle too, they can have common tangents. So all of this can cause some calculations to take place. That is one interaction. Let's look at another interaction now. Now, when you have contacting circle, it means like they can just touch externally like this, or internally. They meet at just one point. They meet at just one point. And by the time you look at this, the distance between their radii and their center is equal to the radius of this one plus the radius of this one. Do you understand? The distance between their centers, because it's not that does not necessarily mean it will be the perpendicular distance. But if this one is A, B, so the distance AB is equal to RA plus RB. For this one too, if the distance is A and this one is A, you can see. So the distance AB is equal to RA minus RB. So this is internal contact, this is external contact. And you can see they have common tangents. Just like the previous one has common chord, they have common tangents. You can see. If it is internal contact like this, there won't be, okay, this is one tangent. But in this instance, you can also have external tangent like this. This is the touching tangent. You understand? And this one. So we can have it like this. So you can see what kind of calculations might come up with this. Now, another thing we can look at is when we have them far apart, that is, they are not touching, they are not intersecting. We can have them also non-touching, non-contact, non-interacting, like this. You can see. So the distance here might need some other, you might need some other information to be able to calculate the distance AB. And they can also have common tangents. They can also have common tangents. You see? And they can also have this tangent too. You see? You can see the kind of tangents they can have. So we call these ones direct tangent. This one is a transverse. So with this, you can do so many other kinds of calculations. So many kinds of calculations. And by the time you go through one or two examples, you will see how easy they can be. And very interesting. You know that this, I also know that this one too. And then this one, yeah. So, with all this known already, we can solve so many problems easily. I believe that with what we have done, we should be able to solve problems easily without any itch when it comes to circle, measurement, and geometry. Thank you for being patient so far. Kindly like, share, comment please, and then subscribe if you haven't. So do whatever you know will encourage us so that we'll be able to bring more to your views. If you have any question, you can direct it to us through the comment section and the link in the description below. Whatever you know that you need to do, any kind of advice, encouragement, please, they are welcome. Even criticism, they are not shying away from it. And I would like you to know that we also offer our services for students via YouTube, Google links, and whatever. Zoom. So anytime you are interested, you can contact us as well and we can discuss. This is already being done with so many people and you can see the improvements in there. Thank you very much. I appreciate you all.